Hello dear colleagues, my name is Savelev Alexandr, and today I'm glad to present our work tracking small objects in global motion conditions for an ornithological monitoring system. This research was conducted together with our colleagues from St. Petersburg Electrotechnical University LTI, ITMO University and State Petersburg State University. Automatic bird tracking in video is a key task in applied ecology and biomonitoring observation. It helps researchers analyze migration patterns, estimate populations, and understand variety behavior over large areas. However, real-world monitoring is very different from laboratory conditions. The video scenes are full of motion, both from the camera itself and the environment. Backgrounds are complex, objects are tiny and low contrast, and birds often overlap or disappear behind trees and clouds. Another challenge is performance. Such system must work close to real time, even with limited computing resources. Previous studies have combined infrared and radar sensor or modified YOLA V8 models for bird detection in near protected areas. But none of them barely address camera motion, which significantly distorts the optical flow and breaks most conventional trackers. Our contribution is a tracking method that stays stable under global camera motion, background changes, and scale variation. It appears real-time on RTX 3090 GPU using pan-tilt optical system, and it supports long-range monitoring up to 2 km of medium-sized birds. In the related work, there are several categories of approaches. Modern deep learning methods, for example ST-Motion TinyDet, TET or CTF-YOLA, show excellent accuracy, but they are computationally heavy and often unsuitable for real-time streaming. Classical methods such as KCF, SRT, or DSFNet are much faster and work on weak hardware, but they are less robust and require frequent reinitialization when the object changes appearance or moves unpredictably. Our baseline system uses HUG plus KCF plus Kalman filter, a traditional combination that is effective but unstable when the target's motion becomes irregular. In contrast, the proposed approach combines neural segmentation with a Kalman filter, making it more adaptive to the chaotic and nonlinear flight patterns typically of birds. Let me briefly describe our tracking pipeline. It consists of several key modules. SSD-ATSAR detector is used for global initialization and local confirmation. Segment Anything Model 2 performs segmentation, providing precise object boundaries and helping partial occlusions. A third-order Kalman filter predicts the motion, not only position and velocity, but also acceleration. Finally, a pan-tilt controller keeps the camera aligned with the predicted target position. The process works as follows. We start with global detection to secure the target. The Kalman filter predicts its next position and defines a region of interest. Inside this region, SAM2 performs segmentation and SSD-ATSAR detects the target again. Their results are compared by intersection over union. If they agree, we update the Kalman filter. If not, we rely on prediction until confirmation returns. This hybrid design combines segmentation precision with Kalman robustness and achieves stable real-time tracking, even under strong camera motion, scale variation, and irregular bird trajectories. To evaluate our method, we performed an experimental study. The goal was to measure how reliable the system tracks birds and how fast it processes video. We compared two methods, a classical baseline, HOG plus KCF plus Kalman, and our proposed approach, SAM2 plus Kalman filter plus SSD-ATSAR. We used full HD videos recorded in realistic ornithological conditions, forests, russell areas, urban scenes, and moving cameras. Two metrics were used. Tracking failures when the tracker lost the target and must reacquire it, and processing speed measured in frames per second on NVIDIA RTX 3090 GPU. In these experiments, the bird often changes its size dramatically, from just a few pixels up to hundreds, and sometimes merges with the background. Our method successfully tracks these transformations, maintaining a stable trajectory even when the bird changes shape from compact to widespread wings. It also remains robust under irregular motion, where classical methods usually fail. This combination of SSDR detection, SAM2 segmentation, and Kalman prediction makes the system uniquely capable of handling real-world bird tracking scenarios, where movement is unpredictable and visual background is constantly changing. Our tracker had a failure rate of about 5 times 10 to the minus 4, while the Hawk Plus KCF tracker reached 2 times 10 to the minus 3. In terms of speed, the classical tracker is significantly faster, but our system still runs at 21 frames per second in Full HD, which is perfectly sufficient of the real-time monitoring. It also shows greater robustness to occlusions and unpredictable motion, for example when a bird briefly disappears behind a tree or changes direction abruptly. Even very small objects, around 5 to 5 pixels, can sometimes be tracked if they have high contrast. Overall, the proposed tracker ensures fewer dropouts and smoother tracking in all tested scenarios. To summarize, our method integrates SAM2 segmentation, SSDR detection, and a Kalman filter into unfair real-time tracking system. It maintains stability under global motion, handles occlusions, and adapts to changes in object appearance. They achieve better performance than the baseline. This level of accuracy and robustness allows deployment in real-time ornithological field system. Beyond research, this technology has strong practical value. It can support biodiversity studies, habitat monitoring, and migration analysis. In the future, we plan to optimize the system for edge devices, such as JSON or FPGA platforms, expand datasets with different speed size and weather conditions, and evaluate additional metrics, including long-term reidentification and trajectory continuity. We also intend to compare it with other lightweight state-of-the-art trackers. Thank you very much for your attention. If you have any question, I will be happy to discuss them.